So basically, you all know Professor Kamal. So we have just reinforced this a little bit. Professor Kamal and Yasuton, they are here for a visit for some time within our European project RESET, which is about basically risk analysis of offshore structures, offshore installations and everything. So it's very, very broad-based. And what we are working on is basically everything which has to do with risk analysis and uncertainty quantification, where we try to connect to all the other team members and see if we can start some collaboration on this. So Ahmad is based in UKM, which is in Kuala Lumpur in Malaysia, and he comes from a strong mechanical background, dealing with all kinds of problems in fatigue analysis and even beyond this. And he's a key member in the Malaysian society, which is basically a partner society of the German Association for Computational Mechanics. That kind of community exists in each and every country, and that is connected to the International Association for Computational Mechanics. And Professor Kamal is a key person in that community in Malaysia. So with that, I would like to hand over and ask you for your presentation.
Yeah. Thank you very much, Professor Michael Beer, for the nice introduction. I am very lucky to be here. I would say this is my second long stay in Germany. Previously, I was in Duisburg for 6 months. So this is 2 months. I think it is sufficient, hopefully. So this is the title of the talk. Almost 70 pages, but I will cut short due to time constraint. Luckily, I have only one sheet for equation. The rest are figures and photos. And hopefully I can skip most of the figures and result. But I have to put it here because it is a continuation unless you are missing one by one, but I will skip that. I mentioned to you I have 70 slides, but if you have the difficulty of continue, I will probably finish before the end of the slide. But you can download my presentation from this. So if you have the smartphone, just scan the QR code, then you can have that. It may take some time to download because this is 70 slide. So that is the outline, problem statement, metal forming, fatigue, crack growth, deterministic, probabilistic, and experiment. And finally, concluding remarks. So this is the, as Prof. Michael Beer mentioned, this is part of the RESET program, which is, I'm very happy to be in the group. So this is Leibniz and this is UKM. This is 4 years program until 2021, which consists of 5 from Europe and 4 from Asia, China, Southeast Asia, and also Thailand. So in brief, the project is about this: the fracture, fatigue, and corrosion, uncertainty modeling, design, operation, management, probabilistic, and final element, which the group has all the expertise. I'm very fortunate to know Prof. Michael Beer and also other, which Professor Jin Wang from Liverpool John Moore University is the head right now. All right, to start off, everybody knows the deterministic approach, which you have all the formula and also uncertainties, which normally people, until now, they are still working on deterministic, full of formula here and there. And sometimes engineers just take the safety of factor which may be under or over designed. And to complete all of this, the computational process work in parallel with all of this deterministic uncertainty. With the emerging of Industrial 4.0, the focus right now we are on this area, which they call it additive manufacturing, which I give you an example of this. This is the one with all the components. It is almost impossible to produce this component using conventional process. What is the conventional process? For example, you melt the metal and then pour into the die and come out with the component. That is the traditional one. Having the Industrial 4.0, they are using metal powder to produce this. For example, this component, the engine component, and most of these are maritime component. So this is the project that we are focusing on. Another example, the biomedical component. Imagine how you want to produce this component by using conventional. It is almost impossible. And the emerging technology now, Industry 4.0, they are producing this type of component. Second process is by having high pressure torsion. This is the specimen. You just press and squeeze that component. Why you have that press and squeeze? Because this is the original one. After first process, you have the strength and then fill around here. But when you have press one revolution, it will increase the strength but very brittle. If you have 5 revolutions, you increase the strength also and also increase the ductile. So the problem with that is you have different in hardness or density. So this is the process. You produce a structure and finally you have to know the properties. This is what we in the group focusing on. So another problem is the crack when we produce that. So the challenges is inhomogeneity in hardness or density. If you produce a component, maybe very high at the end and loose at the end here. So it is not good. So that is the problem. Second one is the multidiscipline issue. You have friction, you have heat transfer, and also variation in parameters. Behind this process, I can say a lot of mathematics behind this, but I'm not putting any mathematics in here. The early process, we have that height, and finally, the final one, we have that size. All right? Imagine this is in elastic region. Beyond this are in plastic region. A powder, initially they have cohesion here, and then the failure criteria for initial one is somewhere here. So I would say this is belong to this, and then after pressing, the component become dense and harder. So become harder, so they have bigger elastic. So the second one will be this. So this is belong to this. Right? So finally, when it become a solid, can you imagine a solid material? They have this failure model. This is similar like von Mises. So for this is von Mises failure criteria. The rest, they call it Roscoe or CAP model. This is Roscoe, this is CAP model combined together, and it increase during the densification. So this is similar to soil mechanics problem, elastoplastic or plasticity theory. So the equation, they have to have large displacement model, material non-linearity, friction, because here we have the interaction between the metal and metal. So if you are in civil engineering, you have interaction between soil and structure. So you have the interface between that, and you have friction when they have the densification. So along that, you need to have elastoplastic material model with large displacement, because this is the initial size and it become smaller size. If you're using conventional finite element, it will not work because it is large displacement. And if you have friction, you have to put algorithm on that, the interface between metal and metal, or the powder and the dye, and also heat conduction. So this is all in multidiscipline calculation. So this is another view of the process. This is the initial one, and then you press here, you have this density contour, and then when you release the punch, you have a spring back because recovery of the elastic, and then you press for the ejection of that, you have friction along here. Imagine if you want to produce a component, it is in room temperature. After pressing, you cannot hold the component because it is hot. You can see the variation of density or hardness from initial to final. So this is another view of the density. It starts with 0.4 relative density. So 1 is for solid. So this is powder. Relative density from solid, it is 0.4 initially, and then increase to 1. 1 is solid, right? So different yield criteria. This is more Coulomb. I think civil engineer knows more Coulomb, or N cap. This is for dilation. This is for densification. This is the combine of these both to represent the powder material. This is considered a complex problem, which you have the shape around this corner. So why this is a problem? Because if you can imagine the powder flow from top to bottom, let's say from here during compression, and will initiate the crack. I give you an example of that. So for example, this is initial, and then press from the top, and then press from bottom. If you can imagine, if you can see from this contour, they have a crack initiation at that corner. So from there, how you want to model the crack? We did the opening here. Let's say this is the original one. If we follow the conventional finite element, the crack will go through here. But if it is in the calculation, the crack will follow through here. The mesh will remesh again to this direction. So they will remesh again this mesh to have the true direction of the crack. Right? They will remesh. So in the crack direction, this is the one. So they will remesh with that. This is the direction. So we have the theta here, And also another parameter which is important is the A, which is the crack length. So let's say this is the crack length. So we follow that. And then another calculation, they will open another new crack. So this is the crack propagation, which is opening. The problem may be in the component is the shear crack. So we tackle on that also, but the shear we cannot see, but the opening we can see. From initial one and then higher and then higher. Another verification with other people work. If you can imagine, this is other people work. They have too dense of mesh, too many mesh to simulate, and what they have here, they are not having opening, but the mesh still here, but they make it black. So we able to produce the how we can physically see the opening of the crack. Another work from our student is to verify with experiment. So this is another verification. This is other people work. This is our work. And we did also with discrete element. Imagine the material made from brittle, let's say glass, how they break. So they break here, so it shows almost represent the crack behavior. So finite element plus discrete element. When we put the Monte Carlo plus one of the option of crack propagation using BZ, so we have a cloud of result compared with deterministic. So huge difference between the deterministic and also the Monte Carlo. This is a test from other people work. When we increase the loading, it is obvious the failure is increased. I'm not focusing on this, but I want to highlight here, when we incorporate the fatigue, there are two types of loading. One is constant amplitude loading and also variable amplitude loading. The constant is not really difficult, but the difficult is the variable amplitude loading. The constant amplitude loading is just you have the loading with a constant the upper and lower loading, but the variable loading is you can have variable. Initial work, we try to have this loading, the upper decrease and the lower stay here, and we did experiment on this, and we compare with other model which normally calculate in fatigue. So the problem is the well-known formula for fatigue is not similar with the experiment. Commercial package on fatigue, normally they are using the model that is already in place. So when we compare with the experiment, it is huge different. And then we did another experiment on that and compare with the calculation. So we have that. How much variation of the experiment with the comparison of the fitting line which normally they put into the software. So in the middle here is the fitting. Let's say we take one line here, and then how much different the value that you want to take. So this is the range of parameter. All right, so we make the experiment and also the simulation. using probabilistic and deterministic. So that is the framework. And if we have money, if we have grant, so we focus on the experiment. I think if somebody want to continue, don't do the experiment. We have all the data, so take all the data, do the simulation. All right. I have all the data on the simulation. On the experiment. Just take that. Another option of the crack is using the global and local mesh. So this is the one. This is the only formula that I have in this slide. So we have the global mesh and local mesh, and this is to reduce the mesh of the domain. So you have only small area for the crack, which very dense mesh, and the rest remain similar. Normally we have two types of crack, which is surface crack. This is on the surface, and this is embedded crack, which is in the middle. So normally there are two cracks, whether it is on the surface or in the middle. So we did the experiment. Let's say here, this is the type of crack, whether it is elliptic or it is semicircle. So we did both on that. We have the result. It takes time to explain, but I want to highlight this result. All right. So we have the variation of that, rather than in the middle here using deterministic. I want to highlight here. This is the one. All right. This is from other people's work, which is deterministic. We put the deterministic in our simulation. So you have both, which is good and in good agreement. However, when we put deterministic there, so we have that range from here to here. So you have that range. So this is the stress intensity factor, SIF, or K, which govern the crack. This number shouldn't be more, otherwise the component will fail. So if you take that, there is a remaining from here. If we consider only deterministic, we not consider all the probabilistic, we have this range. It looks safe initially, but we have this range. And if we put into that, the fail region is 40%. It is huge. So don't undermine the uncertainty of the material. So a few parameters of this very fine of crack mark. They call it beach mark. So this is the one. Again, when we include the probabilistic, we can have this. Why we have that? Because I've already mentioned, it shows shouldn't be more than the criteria, right? Another result, deterministic and other experiment, we have that. So this is from deterministic from other people's work, but when we did, that is the one. So it is a huge difference. The sensitivity of the parameter, maybe some of that very sensitive, some of that not very. Let's say this is the one not very. Another result, this is multi-crack, not only one crack. maybe 2 or 3. So this is an example of 2 crack. So you give that result and make comparison with experiment, deterministic, and also the uncertainty of that. You can see the difference with deterministic and also others. So that is the one. Another parameter. Alright, why we need to have that benchmark? Because if you can imagine, this is the crack, initial crack. This is the initial crack. This is the stress intensity factor, which is very important. What happens if the crack increase? The curve of the SIF, the K is different. So it shows how important is the crack size or crack shape. Another result, if you have semicircle, increase the shape until semicircle, from elliptic to semicircle, so you have different. Initially you have this, right? This is the one I mentioned to you, the experimental work. It takes 2 years to produce this. It looks simple but difficult to have, and somebody want to continue, just take all the data and then do all the analysis. This is the benchmark. 2-point bending, 3-point bending, whether it is embedded, this is embedded crack, elliptic, you have this, elliptic, the other side, you have different shape, and then fracture behavior, this is pure mechanical, how you want to see the crack, whether it is brittle or ductile due to some loading condition. Alright. This is typical specimen for fatigue crack growth. I see another view of crack fractography. And then finally, hopefully, this is the novelty from one stage to another, from problem statement, objective, method, result, conclusion. We did some corrosion work here, but not have much. I cannot say much. I should acknowledge the student, how many students who contribute to the work, master student and PhD student. Okay, that's all from me. Thank you very much for listening.